Welcome to the Deep Dive. Today we're strapping on our virtual helmets and heading to the moon. We're going to try and solve a bit of a mystery, one hidden in plain sight, or maybe hidden in plain geometry.
That's a good way to put it. Yeah, we're diving into some really fascinating crystal growth research, and it focuses on these tiny, almost beautiful artifacts brought back, 50 years ago during the Apollo missions?
Exactly. So our mission today is to get why iron from the moon looks, well, fundamentally different from the iron we find or make here on Earth.
And it's more than just, academic crystallography. This is really material science trying to crack the code of a unique extraterrestrial environment.
Right. We're zooming in on samples incredibly small, like micron-sized single crystals of iron. They were found in the lunar soil, the regolith, specifically from the Apollo 15 Hadley Apennine site. And the initial analysis, this was decades ago, Clanton and his team did a lot of work here, it revealed something of a paradox.
Yeah, the paradox being purity versus shape. The chemical test showed these crystals were pristine, like exceptionally high purity iron.
Meaning?
Meaning the usual suspects, things like nickel, phosphorus, cobalt, sulfur, they were all way down, below the 0.5% detection limit. So chemically, this iron was about as pure as you could possibly get.
That's pure iron, but structurally?
Structurally, they were rebels, complete rebels. If you look at pure iron crystals made in labs here on Earth, or, standard iron in most meteorites, they follow the rules. Simple shapes.
Predictable shapes.
Very predictable. Their morphology, their shape, it's governed by these low-index crystallographic planes. Mostly the familiar planes. Sometimes you see a bit of...
Right, the sort of standard crystal faces.
Exactly. In crystallography, we call those the stable or preferred growth faces, at least in a terrestrial setting. But the lunar samples, they just threw the rulebook out.
How so?
Well, the early studies reported that these tiny lunar crystals showed off 6 of the 7 possible forms of what's called the holosymmetric class M3 barum.
Whoa, okay, that sounds complex. 6 out of 7.
It indicates an astonishing level of geometric complexity. I mean, far beyond anything natural iron usually bothers with.
So that immediately signals something fundamentally different must have happened when they formed, right?
Precisely. Their birth environment had to be unique. And this weird geometry, it was so persistent and intricate that, it eventually drew in modern researchers 50 years later.
So fast forward.
Yeah, fast forward to 2023. Kevin Knowles and Bhadeshia published this analysis. They wanted to specifically solve what had become like a classic crystallography problem, identifying the precise numerical signature, the Miller indices of those really exotic crystal facets.
And that's our deep dive today, how they use some pretty clever geometry old-school techniques, really to finally pin down those indices.
And in doing that, reveal a little secret about the moon's chemical past.
Okay, let's start with the visual puzzle then. The core shape that baffled researchers for so long. It involved the specific, pretty unusual morphology called the deltoidal icositetrahedron faceting.
Yeah, that name is definitely a mouthful. It's important we try and picture it, though. Don't think simple cube.
Right.
Think of a cube, maybe, where the corners have been cut off, truncated, but not just flat cuts. The faces that are formed are sort of kite-shaped or trapezoidal. It's complex.
So we've got the familiar cube faces, but then these other, much more complex faces appear.
Exactly. And these new faces, they're defined by specific planes. That's A. And crucially, the L is significantly greater than the H.
Okay, let's quickly unpack Miller indices for everyone.
Yeah.
The numbers in the brackets, like 100 or 8, they basically define how that flat crystal face is oriented relative to the crystal's main axis, right?
Spot on. Simple numbers like when the face is parallel to 2 axes and cuts across 1, that's your basic cube face. Nice and simple.
And when you get these large unequal numbers like A where L is much bigger than H.
Well, that means the face is tilted, sometimes very steeply, relative to those main axes. And that creates these really complex, you might say, exotic geometries.
Okay. And this created the big challenge, didn't it? Because these crystals are tiny. Microscopic, just a few micrometers across.
Yep. And the original images, taken back in the 70s with a scanning electron microscope, an SM. So what you get is a 2D shadow, basically, a projection of a very complex 3D object.
So how on earth do you go from a presumably grainy 50-year-old 2D photo to figuring out the precise 3D Miller indices, the H and the L?
That's the million-dollar question, isn't it? It sounds like trying to reverse engineer, a complex building just from one blurry photo.
Exactly. And you have to wonder, with those old SM images, how could they possibly trust the angles enough? Enough to tell apart faces that might only be a few degrees different.
That's a really crucial point. And the trust, it comes from the maths, the mathematical rigor, and also the physics of how the SEM actually works. They could leverage the fact that these crystals are so tiny and the magnification was so high.
Which simplifies things how?
Well, think about perspective. If you take a picture of something close up, lines converge, right? That's perspective projection. But because the crystal is minuscule compared to SEM's optics, the electron beams coming off the faces towards the detector are essentially parallel.
Okay, so no perspective distortion, effectively.
Pretty much. It means they could approximate the whole setup as an orthographic projection.
Orthographic projection. Right. That means treating the image as if the 3D shape was just pressed flat onto the 2D image plane, like the viewing point is infinitely far away.
You got it. It's a standard technique in crystallography, but it was key here. It makes the complex geometry maths actually solvable. They didn't have to worry about how perspective might curve things.
So you could then set up these projectional geometry equations.
Exactly. They'd model how a theoretically perfect crystal, say with facets, should look in 2D when viewed from some arbitrary unknown angle. Let's call it UVA debut.
So they're basically trying to match a whole library of theoretical 2D projections against the actual 2D image they had.
That's it in a nutshell. It was a serious test of classical crystallography. They had to solve for the specific viewing angle, the UVA dot, that made the theoretical angles and the visible faces match what they saw in the real SEM picture.
That sounds incredibly painstaking.
Oh, it was. And importantly, they had to build in some flexibility. They adjusted the model to account for the fact that, real crystals aren't always perfect. Some faces might be a bit elongated or different sizes. That happens in natural growth.
Okay, so after all that complex modeling, matching angles, accounting for imperfections, what were the prime suspects? What did the geometry actually point to?
Right, so they approached it very systematically. They took 5 different crystal images from the Apollo samples, good set of examples, and they tested them against 6 plausible candidate families of planes, the ones that could potentially form this complex deltoidal icositetrahedron shape.
Which were?
They modeled 12.
Okay, 6 possibilities. Still sounds like a massive amount of calculation, testing each one against 5 crystals from unknown angles.
It absolutely was. Intense dedication, really. But it was necessary because the real answer, it turned out, was hidden in these tiny angular differences.
So what was the final verdict?
The analysis, the number crunching, it concluded that the faceting, this deltoidal icositetrahedron shape, is best described as planes.
Wow. That is remarkably precise and unusual, right? Why specifically, not maybe the simpler 15?
Well, it goes back to that fine angular precision you asked about. The models showed that was the best fit compromise is the term they use.
Compromise, meaning it wasn't perfectly one thing.
Kind of. Look, the difference in angle between a 120 face and a 115 face is tiny, only about 3.68 degrees. Visually, under a microscope, they'd look almost identical.
They're like neighboring orientations on the atomic lattice.
Exactly, and the index, it's at right smack in the middle. It reproduced the average angles measured from the real lunar crystals more accurately than either 14 or could on their own.
How close?
It was just 1.65 degrees away from the orientation and 2.03 degrees away from 14. So this level of geometric detective work proved the faces weren't just, slightly wonky 14s or 15s. They were genuinely this other highly specific high-index orientation.
That's incredible detail from 50-year-old photos. And crucially, they could also rule things out.
Yes, they confirmed the facets were definitely not. That's important because facets are sometimes reported as a minor feature in some terrestrial iron microcrystals. So this lunar stuff was truly different.
Okay, which leads us, I guess, to the big so what? Why does this bizarre index actually matter? Why is this specific geometry so important?
Because, fundamentally, the morphology of a crystal, its shape, is a physical record. It's an atomic-level fingerprint of the environment where it grew.
The environment is the architect. Okay, now the original Clanton studies, they suggested these crystals formed via something called vapor phase crystallization, or v.c.c, in the lunar environment. How does that differ from how iron crystals usually grow on Earth?
Right. So on Earth, we typically grow crystals from a liquid, from a melt, or sometimes through slow diffusion in a solid state. VPC is different. It's when a material condenses directly from a gas or vapor phase.
Like frost forming on a window.
Exactly like frost, but imagine it happening with, say, super hot iron vapor in the vacuum of space. This often happens near meteor impact sites or maybe lunar volcanic vents, places where intense heat creates a vapor that then cools rapidly.
And the unique shape is the fingerprint, the signature of that specific lunar VPC process.
Absolutely. This highly unusual geometry, it can really only be explained or rationalized, as we say, by very specific local chemical conditions during that condensation process.
Okay, local chemical conditions. But didn't we say the iron itself was incredibly pure?
We did. And that's the key. The bulk crystal, yes, super pure iron. But the surface, the very outer layer where growth is actually happening atom by atom, that must have been interacting with trace amounts of other elements or compounds, what we call absorbents, present in that lunar vapor.
So the bulk is pure, but the surface chemistry during growth was complex. How does that surface chemistry end up dictating the final shape?
Okay, let's zoom right down to the atomic level. Imagine the crystal growing layer by layer, atom by atom. Even a mathematically defined face isn't perfectly flat at the atomic scale. It has steps, like tiny terraces.
Right.
And at the edges of these steps, there are special spots called kink sites. These are like the prime real estate, the most energetically favorable spots for new iron atoms drifting in from the vapor to land and stick permanently.
So the kink sites are the atomic landing pads.
Perfect analogy. Now imagine there's some trace element in that vapor and absorb it. Maybe silicon, maybe oxygen, we don't know for sure. If that impurity preferentially sticks to certain types of crystal faces, maybe the simple faces.
It blocks those landing pads.
Exactly. It acts like a highly selective atomic roadblock. If the impurity gums up the works on the low-index faces, like 1, it slows down or even stops growth in that direction.
And if growth is blocked on the simple faces?
Then the crystal is forced to grow faster in other directions, developing these steeper, more complex, higher-energy faces, like the exotic geometry we see. Growth just proceeds more rapidly where it isn't blocked.
So the trace impurities in the vapor act as a kind of filter, forcing the crystal into this unusual shape.
Precisely. The source material actually draws a parallel here to studies on other materials, like iridium. They've shown that faceting on high-index surfaces, like iridium-210, can be entirely driven by these chemical effects, by absorbents sticking at the nanometer level.
So these trace vapors in the lunar environment, whatever they were, they acted as a kinetic filter. They drove the pure iron to crystallize in this high-index, energetic, and really quite beautiful form.
Yes. That complex geometry is literally an indelible record etched in iron, a record of the vapor chemistry that surrounded it billions of years ago or whenever it formed.
That's a phenomenal synthesis. We've gone from a grainy 2D image of a tiny moon rock speck to using math to identify a super-specific atomic plane, and now understanding that the reason that plane exists was dictated by invisible chemistry on the moon.
It's pretty neat, isn't it? What's fascinating, though, is that the knowledge is now, well, crystallized, so to speak. We know the result, the geometry, but it does raise an important follow-up question.
Which is?
We understand the likely mechanism, this vapor phase crystallization driven by surface absorbates. But do we know the exact nature of that ancient lunar vapor? The specific impurities? Or the precise temperatures involved?
So the study nailed the geometry, but the exact historical chemical context is still a bit fuzzy.
That's right. Pinning down the precise nature of that vapor, the specific elements that acted as the roadblocks causing this unique morphology that remains elusive. This research confirms the moon's environment can produce geometries we just don't see typically, and can't easily replicate with our terrestrial models.
So simulating the exact kinetics and thermodynamics of that ancient lunar vapor, that's still a huge challenge.
A massive challenge for future work, yeah, for material science and planetary science.
So the big takeaway seems to be that a crystal's shape, its morphology, isn't just about what it's made of in bulk. It's exquisitely sensitive to the local physics and, critically, the local chemistry present right at the moment of its birth.
That sensitivity is absolutely the key. These lunar crystals are like tiny atomic documents recording an environment we're still trying to fully understand.
It makes you wonder, doesn't it? If the shape of simple, pure iron can be changed so dramatically by tiny amounts of transient chemicals in space, what subtle complexities are we missing in materials grown right here on Earth?
That's a great point. What else is the solar system, through the geometry of its tiniest structures, trying to teach us?
Something to definitely mull over. Thanks for that fascinating dive into lunar geometry.
My pleasure. It's amazing what you can find in 50-year-old moon dust.
Indeed it is. Join us next time for another deep dive.